So we're going to go over transcriptional modeling today, and we'll start with a visualization. So here is our setup. We have a promoter in green and our open reading frame in blue, our RNA polymerase in yellow, and our activators in green. So first let's address basal activity. This will happen with any RNA polymerase. It has some affinity for promoters just on its own. So it will just spontaneously attach to the promoter and transcribe DNA without any transcriptional effects. This happens some of the time. We call it background or basal expression. Now, as for inducible promoters, these tend to have low background expression until these two activators here act cooperatively. In this case, our cooperativity parameter is 2, to activate the RNA polymerase and increase its affinity for the promoter, and it will tend to transcribe more when bound. On the other hand, you have a repressible promoter where the RNA polymerase is by default transcribing the DNA. It has very high affinity for the promoter. And then you have these repressors that can bind to the RNA polymerase and actually decrease its affinity for the promoter. Again, these are acting cooperatively. So here again, we have cooperativity is 2. But in either activation or repression, this number can be anywhere between 1 and dozens. And since the affinity for the DNA has decreased, the RNA polymerase falls off and it stops expression. Let's actually model our transcription. So let X denote the transcription factors, and these have a cooperativity of N, and let P be the promoter for a specific gene. So we're trying to find out how these factors contribute to the transcription rate and how we can mathematically model this. So first we need to derive a chemical formula for this process. So per our visualization from before, we notice that we have a promoter. We have N activators, which are denoted X, and they eventually form a complex with N X activators and or repressors and the promoter. And this whole equation has a dissociation constant Kd. And Kd is defined such that for reactants A and B associating into AABB, aka NE complex, then you should have this equation hold. And this just comes from chemistry equations. It's the proportion of dissociated products to the exponent of their cooperativities over the concentration of the complex. So we can use this association constant to help determine our modeling, right? And we use our chemical equation and the dissociation constant equation to write this equation to help us derive the modeling for transcription. So we have the concentration of the promoter times the concentration of activator to the power of the cooperativity over the concentration of the complex. And that equals the dissociation constant, since we have our individual elements on the top and our complex at the bottom. Now let's derive the actual promoter activity. So promoter activity is determined by the fraction of occupied promoters, and this differs from activators and repressors. We will go over that later. So for now, we just want to know the fraction of occupied promoters, which is given by the complex, over the total amount of promoters in the system, whether they are bound or not. And we are given the previous equation for the dissociation constant, as well as our just simple equation saying that our unbound promoters plus our bound promoters equals our total promoters. So we have our dissociation constant equation on the left as it was before, and we're going to define theta as our inducible expression rate, or repressible. I suppose it's just regulated expression rate. And then we have the fraction of bound promoters, which is the pxn over p tot term. And then we have k, which is some scaling factor, since it's not exactly related to the fraction of occupied promoters, so we add in this scaling factor. So we rearrange the equation for theta to have p tot on the bottom instead, bp plus pxn. Note there is a typo there, there should be a k there. And then we also rearrange the dissociation constant equation so that we have it solve for the concentration of the complex. So here I've just rewritten these equations. And then we just plug in the equation for the complex into the equation for theta. So note how I just plugged this in here. So then you get this complicated equation here. But if you multiply it by kd over p over kd over p, then you will note that many terms cancel out and you get a much more simplified expression like this. So let's now look at inducible promoters specifically. The activity of an inducible promoter is proportional to the fraction of bound promoters. So exactly what we solved, theta. So let f of x be the transcription rate given x concentration of the activator. It will be proportional to theta. But we also have to consider basal expression. So let's let k prime be the background transcription rate. And then we just substitute for theta, and then we get this final equation for inducible expression. So now we're going to talk about repressible promoters. So the activity of a repressible promoter is proportional to the fraction of unbound promoters, or k minus theta, because remember, theta is just the fraction of bound promoters scaled by k. So we're essentially doing k times the unbound fraction. So let f of x be defined as we did earlier, and we're still going to consider basal transcription. So here we have f of x is equal to k prime plus k minus theta. So now we have to substitute and rearrange for theta, and you can actually take that and simplify it further down to just f of x is equal to k prime plus k times kd over kd plus x to the n.